Welcome back. So today is the fourth lecture on financial mathematics for actuaries. Here we are essentially digging into the same concepts of I and D and present value V. However, we will exploit them in a more mathematical manner. So let's understand what is today's roadmap. First, we will connect this interest with discount, which we have done already intuitively. We will do some mathematical theory behind it. Then we will prove the inequality that D is less than I, and then we will introduce one discount factor identity V equal to 1 minus D and derive some related identities related to D, V and I, and then we will solve the problem for unknown time n using the logarithms, the most powerful tool. The reference mapping is again the same, Brouwerman section 1.5 and Chan and Say sections 1.5 and 7. Okay. So let us dive deeper into today's class, where we are actually exploring the relationship between I and D, and in turn we will land up in proving 4 to 5 identities. So here is the basic connection. When we are traveling forward, we are looking at the future value of money. When we are traveling backwards, we are looking at the present value of money. So at any given point in time, I will be the interest which will be charged or given to you based on the start balance. Okay. When you talk about D, which is the discount rate, it will be charged or given to you on end balance. So this is the key principle that can be summarized into one tiny equation, which is basically start into 1 plus I is equal to end, okay, or end or start into 1 plus I is equal to end. These both describe the same transaction. One is going forward, another one is going backward in time. So let us understand why D should be less than I. So if you have taken a loan that grows to 110, that means the interest amount or the interest amount that is A1 minus A0, when I am referring to capital A, so here A0 is equal to 100, A1 is equal to 110, and then I am referring to the difference between these two, which is A1 minus A0, that by definition is I1, and that I1 is 10, correct. So when I calculate the interest rate as per our convention I will use the starting capital, which is A0. So I will have I1 by A0, that will be equal to 10 upon 100, which will be 10%, 0.10, which will be 10%, correct. Similarly, when I will calculate this D, according to our assumption, we will use that end capital. So here this is the start and this is the end. So I will use end capital. So it will be I1 divided by end capital, which is A1, and then it will turn out that this is 10 upon 110. That will give me something like 0.0909 and so on, right. So that actually becomes the discount factor of 9.09. So the basic question that we are trying to solve here is why D is less than I. So if you translate this into a notion of present value and future value, you can say present value will earn the interest and that will give me the future value, correct. So essentially this particular term is always going to be positive. Therefore, this present value and future value will have a relation which is present value is always smaller than future value, and therefore whenever I take the denominator which is of higher value, so this present value is denoted by A0 and the future value is denoted by A1, then we always have a relation which is of this form, and therefore you will always have a heavy denominator when you are calculating a discount factor, and that is why D is going to be less than I. So now we have proved that D is always going to be less than I. Now let us try to understand the algebraic link between D and I. Yesterday's class we have already derived this formula, D is equal to I upon 1 plus I. Let us quickly revise what we have done in yesterday's class. So essentially what we had is D, which is the discount rate, which will be the interest rate earned upon the accumulated amount function at the end of the period, that is A1. We saw that this interest rate earned was A1 minus A0, but it can also be seen as the interest accumulated on the initial capital. Then we saw this A1 is nothing but 1 plus I times A0, and then we got rid of these two A0s, and therefore we received a formula which is D is equal to I upon 1 plus I. So let us explore this link between D and I. Right now what I am doing, I have just derived the formula for D in terms of I. It will be interesting to have a formula for I in terms of D. How can I do that? Can I do that using this particular identity? The answer to that is yes. And how can I do that? So essentially you look at this identity, it has I at two places. So D into 1 plus I is equal to I. If I multiply y by 1 plus I on both sides, I will get this. So what is my goal? My goal is to write I in terms of D. So I will take away the terms of D and I will use the terms of I. So D plus D times I is equal to I. So what I can do, I can take this di on the other side, so that all the terms containing I will be on one side. So it will be I times 1 minus D, because taking on to the other side is equivalent to subtracting id from both sides. So I into 1 minus D. So what I got, I is equal to D upon 1 minus D. Wonderful. So what I have received here is D is equal to I upon 1 plus I, or I is equal to D upon 1 minus D. Can we do it in some other way? So for example, this I can write as 1 minus 1 upon 1 plus I. I upon 1 plus I can also be written as 1 minus 1 upon 1 plus I. In that case, what I have, I can easily write D, or 1 minus D is equal to, I have taken, so basically I have added 1 plus I on both sides and removed D from both sides. So that will give me 1 minus D is equal to 1 upon 1 plus I. And that if I take it on the other side, I will get, so 1 minus D is equal to 1 upon 1 plus I, and then you can easily take this 1 plus I on the other side and push 1 minus D on the other side. So 1 plus I is equal to 1 upon 1 minus D, correct? And then you take this on the other side, so I is equal to 1 upon 1 minus D minus 1. What will that fetch me? It will again give me D upon 1 minus D, correct? So I have shown you two ways to establish the same identity, I is equal to d upon 1 minus d. So one way is shown here. Now let us try to explore the next topic, which is the most useful identity, and I have already given you a glimpse of it when I wrote that di upon 1 plus I is 1 minus 1 upon 1 plus I. So that essentially comes from the fact, so we already have seen this I upon 1 plus I is equal to 1 minus 1 upon 1 plus I. But this 1 upon 1 plus I, in our previous lecture we connected this with V, which was the present value, right? Okay, so then we have established the identity that D is equal to 1 minus V. If I rearrange, I can write this V as 1 minus D. And we already know that this identity is powerful because it will help me to calculate the present value, right? So its present value is actually future value into V raised to n. So future value, if I use for this particular formula for V, is 1 minus d raised to n. And now we will actually see how given d you can calculate the present value, or given V how can you use the discount factors. So here is a problem where I am asked to find a present value of 5000 which is due in 10 years. So after 10 years the valuation is going to be 5000 if the effective discount rate D is 6%. How will you solve this? Okay. So let us understand the problem first. The 5000 valuation that you are seeking is going to happen in 10 years. Okay. And let us go back to the previous slide and see the connection. I have been given a discount rate which is D, and I have been given the future value. Okay. So how will I calculate? So one way is very simple. So I will first use, I don't know all these tricks. I will take this D equal to 6%. I will use my I will use the relation between I and D, which is essentially I is equal to D upon 1 minus D, which we derived using two relations. So that we will use, and if you use that, you can easily see that this D 6% being used here, and then 1 minus D being used here, and you got the final interest rate of 6.3%. and now you use that formula 1 upon 1 plus I raised to 10, that formula you use, and that's what will give you this particular thing, which is multiplied to the future value of 5000, and you will get the final answer. However, if you look at the previous slide, then you easily know that this D is given to be 6%, so the discount that we are going to give V will be equal to 1 minus D, and from that relation you can simply substitute present value is future value into V raised to 10. So if you use this V is 1 minus D, you get this 1 minus 0.06 raised to 10, and then you simply get this 0.94 raised to 10, and just calculate it on your calculator. You will get the answer to be 269283. So how simplified is this calculation? Roughly in two calculations you got the answer. Here you had to do all these things. So this is one effective way of solving the problems by memorizing the identities. So let's move further and try to prove some more identities. So here in this case we are subtracting D from I, and this is a very crucial identity. So when I subtract D from I am essentially looking at the difference I minus D. So but this D is nothing but IV. We have already proved that. So I get I times 1 minus V. Now what is 1 minus V according to me? We have proved this identity. 1 minus V is D. Therefore what I can do is I can say 1 minus, if I put 1 minus V is equal to D, I minus D is ID. That means difference between the interest rate and discount rate is equal to the product of these two. Okay, and this is actually a very important true or false question in your exam FM. So the wording will say the difference between the rates equal to their product. So this you should always remember, and this is a very important identity for exams. Okay, so let us now handle the slightly difficult problem, which is I want to answer when will the future value double, or I want to see how much, given this interest rate, how much time span will I require to achieve my target, right? So this question can be seen in a mathematical form in this which is posed on this slide. So I have some value, I have some amount, and if I want to double this amount, how long will it take for the interest rate I? So that can be easily written in mathematical form as 1 plus I raised to n is equal to 2, because as we mentioned earlier, the multiplier here is in terms of units, and that will give me amount, but this is something called accumulation, right? So for unit amount, so this amount is assumed to be 1, how long will it take to double the amount, right? So that's the question that we are posing. So let us try to answer that question. So one main pain point that I have is this exponent that I have. So is there any operation which will bring this exponent in the linear scale? That's the first question that we should answer, and the answer to that is yes, affirmative answer, which the tool is natural logarithms. You take log of this, then you will get the exponent in the linear scale. So we will use this tool, and using this tool what we will do is we will start with this, take a log on both sides. So if I take a natural log, I will get ln of 1 plus I raised to n is equal to ln of 2. Then because you already know that ln of a raised to x is equal to x times ln of a, I will use this rule. So this is ln of a raised to x is x times ln of a. I will use this rule and I will take this onto this. Okay, so it's n times ln of 1 plus I is equal to ln of 2. And now, do I know interest rate? Yes, I know interest rate. Do I know what is ln of 2 and what is ln of this number? Yes. So effectively what I am saying is I can solve for n. If I know, give me some interest rate, I will tell you how much time will it take to double. So let us try to do it on a computer or on a scientific calculator. So on scientific calculator, if you consider interest rate to be 8%, you have to simply use this functionality of scientific calculator, where you will first press the number which is the double, so 2, then take the natural log of it, which will give you the display as shown here, 0.6931. Then because it's 8%, so I will always talk about 1 plus I, so I will talk about 1.08, which is 1 plus 0.08, so 1.08, then take a natural log of it as done here, and you will get the display to be equal to this. Then you divide 0.6931 with this particular number, and that will give you the display as shown on the calculator screen like this. Okay, but this is with help of calculator. What if you don't have a calculator and you just want a crude estimate? In the next few slides we will demonstrate that as well. Okay, so that slide is basically the rule of 72. So this is a mental math trick. It doesn't work for all ranges, that's a disclaimer, but however whatever interest rates you are given with, it will mostly work. So the trick is, if I want to find n for doubling the numbers, I will simply take the interest rate, say 8%, and now I will multiply it with 100. So 8% multiplied with 100 will return me 8. Okay, and then I will divide 72 by whatever interest after multiplication by 100 I received. So 72 by 8 should give me 9, and now you can see how close is my approximation, 9.006. So I am remarkably correct. However, a disclaimer, this particular trick, the rule of 72, works well between 4 to 12%. You can try your hand on it and you can check with your calculator how close you are. Most of the times you will be fairly close enough. This rule is your coveted tool for calculating the approximations. So let us summarize what we have done. We have dealt with several identities. First, we have mathematically proved that discount rate is smaller than interest rate. Second, we have shown that the discount rate is actually I upon 1 plus I, which is also equal to I times V. Third, V, which is the factor, discounting factor that we are using, is equal to 1 minus D. Then we have shown that the difference between interest and discount rate is equal to the product of interest and discount rates. This is the crucial question that you will get in exam. And we have solved for unknown n. So where we have actually used ln of the growth that we are estimating upon ln of 1 plus I will give me the expected number of years. These are the identities, and finally we gave one rule of thumb, which is rule of 72, which works well between 4% to 12% interest rates. In the next class, we will solve problems based on these identities and the relations that we have developed. See you in the next class. Thank you.